Hey everyone. So this is the 7th lab for our semester-long project, and it's going to be the condensation of benzoin from benzaldehyde. So up until now, we have performed a couple experiments. We've converted our benzaldehyde to stilbene, then to stilbene dibromide, and then to diphenylacetylene. So now, instead of going to diphenylacetylene, we're going to go a different route with our benzaldehyde. We're going to take our benzaldehyde and condense it to form benzoin. So all of this can be found in chapter 48 of your lab manuals. So up here we have our benzaldehyde molecule. It is a single benzene ring with a carbonyl group, an aldehyde more specifically. And what we're trying to do now is we want to combine two molecules of benzaldehyde and fuse them together to form benzoin. So you can kind of see that same structure. So we have the benzoin ring, our carbonyl group, and what was a carbonyl group but now turned to an alcohol. So traditionally, the benzoin condensation is done using cyanide as our catalyst due to its strong basic ability. However, we can't really use cyanide in the lab because, as most of you know, cyanide is incredibly toxic. And just to be safe with the students, we always try to find alternatives or safer alternatives to use in the lab to perform these similar reactions. So if you want to learn how the reaction is done with cyanide, you can actually look at it in your lab manual. But for this case, or how I'm going to teach it, we'll be using thiamine or vitamin B1 as our catalyst. So here you can see is the molecule that we'll be using. So it is actually thiamine hydrochloride. So thiamine normally exists as a salt. And what we do is that when we add some kind of hydroxide or a strong base, the hydroxide can deprotonate our thiamine and produce this new Zwitter ion catalyst. So you can see here is that negative charge that's going to be very important for our reaction. So before we go any further, what you'll notice that many chemists like to do is they like to cut away the parts that are pretty much useless to the actual mechanism of the chemistry. So you can see these long, bulky side groups. What you need to know is when this reaction occurs, these side groups aren't really affected. You're not going to see any charges that move towards to these other groups, or these groups aren't going to be really touched at all. So normally when this happens, we kind of just hide them away with a letter, so R1, R2, just to show that while they do exist, they're not going to be important for the actual mechanism. So for now, all we really need to focus is on this part of the thiamine molecule. So how exactly does benzoin get formed using this thiamine catalyst? So starting off with our Zwitter ion catalyst and benzaldehyde, our negative charge is able to attack our carbonyl group and break it apart, and we get this negatively charged oxygen. Once this negatively charged oxygen forms, it is able to come and take a hydrogen from a water to form an alcohol. And what we're left with is another hydroxide molecule. So that hydroxide molecule that has been formed can come back and deprotonate the hydrogen that was left over. This produces another negative charge, and we can actually stabilize this negative charge through resonance. So here are the two resonance forms of our benzaldehyde thiamine complex. So you can see that the double bond can shift back and forth between these two positions, and we can either have a Zwitter ionic form or a completely neutral form. What's important is that these because of these resonances, it makes the proton a little bit more acidic, which makes it available to perform the next reaction. So because we have this zwitterionic form with the negatively charged carbon, it's going to want to attack the carbonyl of another benzaldehyde. So this is our second benzaldehyde. So the negative charge comes, attacks the cation, the carbon, and breaks the carbonyl group. And here we can see we have another negatively charged oxygen. Because the negative oxygen doesn't like to stay negative, it's going to steal the hydrogen from its neighboring alcohol. By stealing this hydrogen, it'll cause the formation of a carbonyl, and the formation of this carbonyl will break the bond to the thiamine. So like any good catalyst, once this happens, we get our catalyst once again, absolutely no changes, and we come up with a new molecule, benzoin. So to kind of talk about the actual procedure of the lab, so we're going to be using thiamine hydrochloride, about 1.04 grams. To this thiamine hydrochloride, we'll be adding 3 mLs of water, and this will completely dissolve our thiamine hydrochloride. We then add 8 mLs of ethanol, 3 mLs of our sodium hydroxide base so that we can add the hydroxide into the system. And finally, 3 mLs of our benzaldehyde. So once we add all of these together, we just mix the entire reaction and we keep it at room temperature overnight so that we can complete the synthesis of benzoin, because it does take some time. And so it's one of those reactions that you want to leave overnight and let it have as much time as possible to form your product. The next time you would come in to collect your product, they should form these very fine crystals. And in order to collect them, we would use a Buchner funnel or a Buchner funnel. So in the lab manual, it calls for the use of a Hirsch funnel, but it's important for you to kind of recognize the difference. So while a Buchner funnel kind of has a flat bottom, you can see that the Hirsch funnel, you can see that everything goes right towards the middle of the funnel, and in the middle there's actually more of these little pores. It's kind of hard to see. But for most cases, the Buchner funnel or the Buchner funnel is more than adequate. So in some cases, the benzoin may not have crystallized completely and instead develop some kind of oil or takes the form of an oil. So in order to kind of force it to crystallize, because it's important that we get a solid crystal product, all we do is we lower the temperature by placing the flask into an ice bath. By perturbing our oil in this cold environment, by scratching the inside of the flask with some kind of stirring rod, it will basically seed the crystallization, and soon little tiny crystals of benzoin will start to form inside of the flask. Once this happens, you would just again vacuum filter out the crystals away from the liquid, and you would have successfully crystallized the benzoin. Once you've separated and purified the benzoin, you would wash it with a small volume of cold 50% ethanol. And what this will do is benzoin will dissolve in the ethanol, but it is much less soluble in water. So we got to make sure that the ethanol solution is no more than 50% ethanol, and that we cool our ethanol solution in an ice bath before we actually use it. So the ethanol will clean the product, but it hopefully, because it's at a lower percentage, won't dissolve it. And once we have dried our compound, we will weigh it and we can compare it to what we should have gotten in the theoretical yield. So for the benzoin condensation, the major hazard that we'll be working with is sodium hydroxide. Remember, sodium hydroxide is a very, very strong base, so getting this on your skin can cause chemical burns. Something to note is, or something to remember from the very first lab, is that benzaldehyde is very easily oxidized to benzoic acid. So because of this, we might, when this lab is performed, we might actually use a new bottle of benzaldehyde just so that we don't contaminate it with the acid. But hopefully the benzaldehyde that we form in the very first lab is still, I guess, wasn't exposed to any air and should still be pure benzaldehyde. If this is the case, then we can actually continue with this reagent. If you need to remember or kind of refresh on how we purified benzaldehyde, you can go check again back into, I guess, section 6.4b, or go back to the original benzaldehyde purification video. So I just want to quickly go over calculating the theoretical and percent yield of benzoin. So let's say we were to start off with 4 mLs of benzaldehyde and we were able to isolate 3 grams of benzoin. So the first thing we should immediately recognize is that our benzaldehyde will be the limiting reagent. So we can continue our calculations straight up with just these numbers. So first, to find the theoretical yield, we need to actually convert our volume of benzaldehyde to its mass. So remember, to do this, all you need to do is multiply your volume by the density of the compound, and this will give you the mass. So 4 mLs times 1.04, because of its density, will give you a mass of about 4.16 grams of benzaldehyde. So now we just need to convert this into mass of benzoin. So first we convert our mass into moles. So 4.16 grams of benzaldehyde divided by 106.12 grams of, or grams per mole of benzaldehyde. And this will give you moles of benzaldehyde. We know that for every 2 moles of benzaldehyde, we get 1 mole of benzoin, and every mole of benzoin should be about 212.24 grams. So if we just follow along this entire calculation, so 4.16 divided by 1.06.12 divided by 2 times 212.24, we should be left with 4.16 grams of benzoin. Just to make sure, we can cancel out all of our like terms. So grams of benzaldehyde, moles of benzaldehyde, moles of benzaldehyde, moles of benzoin, moles of benzoin. Let me get a laser. So again, grams cancel, moles of benzaldehyde cancel, moles of benzoin, and finally what we're left with, this should be grams, so grams of benzoin. So this should be 4.16 grams of benzoin. So now to calculate the percent yield, we take the yield that we did receive and divide it by what we should have received. So 3 grams is what we isolated. We planned on isolating 4.16, so 3 divided by 4.16, and then we multiply it times 100 to obtain our percentage. And so our percent yield is actually 72%. So let's assume that after we have purified our benzoin, we want to actually check if we purified the right compound. So we analyze it first through IR spectroscopy. So when I look at this compound, there are three functional groups that stick out to me. The benzene rings, the carbonyl group, and the alcohol. So let's start off with, I guess, our alcohol. Normally, when we think of the alcohol, we think of a broad, big stretch. And it's hard to see it here, but you can kind of see that towards the left side, the spectrum is pulled slightly down, and it stays like this for almost all the way up to, I guess, wave number 2000. So this entire marking here is our alcohol stretch. For our benzene rings, we know that we have sp2 hybridized carbons when we have this peak over here, or I guess, sorry, this peak over here that is above the 3000 mark. This little peak over here is indicative of an sp3 hybridized hydrogen, and this peak is actually this one right here. So there's a hydrogen right there. So alcohol stretch is really this big peak here. It should be broader, but this is the alcohol. This is our sp2 hybridized hydrogens. This is our sp3 hybridized hydrogens. Finally, all we're left with is our carbonyl group, which shows up around 1700, which you can clearly see right here. So the IR spectrum is just from analyzing the IR spectrum, we can easily see that we do have our benzoin. And what about the NMR? So again, the NMR is a little bit harder to read. And what makes it even worse is that we have lots of types of hydrogens. So I've labeled here all the similar hydrogen types. So these hydrogens are the same. These hydrogens are the same. But notice how this hydrogen and this hydrogen are not the same. And that's because this hydrogen is closer to a carbonyl group, while this one is closer to an alcohol. So because of this, these two hydrogens have a slightly different, I guess, resonance than these two hydrogens. So we have 1, 2, 3, 4 is our alcohol, 5 is our sp3 hybridized hydrogen, 6, 7, 8. So of these groups, we have 1, 2, 3, 4, 5, 6 that are part of our benzene rings. And so we expect that these should be above our 7 mark, which you can kind of see here. It's really hard to kind of distinguish between these different hydrogens, but we can assume that these peaks here are for the benzene ring. So what's left are the peaks that we have for our sp3 hybridized hydrogen, as well as for our alcohol. So our alcohol is always going to appear pretty low on the spectrum, and it'll appear as a singlet. So we can assume that this little peak is the alcohol. Meanwhile, our sp3 hybridized hydrogen, not only is it next to an alcohol, but it's also next to the carbonyl as well as its benzene ring. We expect this to be shifted more towards the left. So this single peak, because it has no neighboring hydrogens, should be our sp3 hybridized hydrogen. So just to kind of reiterate, the alcohol, the sp3 hybridized hydrogen, so number 5, as well as our benzene ring hydrogens.